Our first speaker doesn't really need an introduction. You might know him as an assistant professor at Princeton, the chief scientist at Together AI, the inventor of the flash attention algorithm. Supriya Rao, everyone.
Hi, everyone. Really excited to be here. This is a really good vibe. I'll be talking about how to optimize attention for modern GPUs. And this is going to touch on a bunch of joint work with some of the folks at Kofax, folks at Meta, and some folks at NVIDIA, some of whom are here, like Vijay, who's leading a hack session. OK, so let's get started. Just a little bit of motivation. Why do we care about attention? Well, there are tons of applications that we need long context, long sequences. So, for example, in NLP, you want to have new capabilities like reasoning over books and play and code bases. In computer vision, you want to close the reality gap, where you want to model really high-resolution images to give more robust insights. And usually, if you use something like Vision Transformer, high-res images translate to long sequences. It could also open new areas. I have collaborators at Stanford who work on audio modeling, video modeling, medical imaging, and their data is naturally modeled as sequences of up to millions of steps. And so the dominant architecture right now, the transformer, has a hard time scaling up to millions of steps. One way you do that is things like ring attention. But the underlying algorithm and the underlying hardware, we still need to optimize for that. And if we can optimize for that, we can open up a bunch of new areas, not just chatbot, but actually things like AI for science and so on. So this is why we care, or I personally care, about modeling long sequences. So what is the challenge? The challenge is that efficiency is a bottleneck, especially if you use attention. So here I'm using context length to mean how many elements in the sequence does the current element interact with. And what happens if you just increase the context length? So that sounds simple enough. Turns out efficiency is a huge problem here. It can slow down or completely stop training. So here's an example of, I'm just taking Megatron LM. This was 2 years ago, running on A100. And if you have context length 2K, you get very reasonable speeds. It's around 50% MFU, 50% of the theoretical max of the device, which is quite good. But the moment you increase context length to 8K, things start to slow down significantly, or you go out of memory. So this is we can't just brute force and increase context length. So we need to scale to longer sequences. And in order to do that, we got to make attention a lot more efficient. So I'll talk about our recent work, Flash Attention 3. Targeting Hopper GPUs, and I'll talk about some of the new features on modern GPUs that we want to pay attention to, things like asynchrony, warp specialization, low precision, and so on. Okay, so a little bit of background on attention. Maybe a lot of you are familiar, so I'll go over this pretty quickly, just so that we're on the same page in terms of terminology. So we have as input the query and the key. These are, if a single head is n by d, where n is the sequence length, d is the head dimension. N is on the order of thousands, or ideally we want to go up to 1 million. And D is a head dimension, which is usually quite small, on the order of around a couple hundreds. So when you multiply them together, you get a similarity score. You do softmax. And this is what softmax looks like. You multiply by the value, which is also provided, to get an output. And turns out the bottleneck is in these intermediate steps, where you have to scale quadratically in sequence length, because you have these large matrices that you need to usually write out, the score matrix and the attention matrix. So our goal is to not have to write these matrices down. And with a little bit of kernel fusion plus some algorithmic optimization, so you essentially use online softmax, you can avoid this. And that was essentially the idea of flash attention. So I won't go over this too much, but flash attention came out about 2 years ago. Back then it was about 2 to 4x speed up over kind of the best baseline, and significant memory reduction. So you can scale to much longer sequences. And this was essentially optimized for A100, right? And when we took that code, this was flash attention 2, we took that code and we ran on H100, we got to about 350 teraflops per second. The H100, the max is around 1,000. So it's about 35% of what the device is capable of. So we essentially took the A100 code and run on H100 and get reasonable speed, but there's quite a bit of headroom. This is at 35% MFU, 35% of the theoretical max. So there's a whole lot more we can do. How do we optimize for modern hardware? And I'll talk about why the Hopper is quite a bit different and requires a different way of thinking about programming. This is joint work with a bunch of folks at Kofax, Meta, and NVIDIA, as I mentioned. A lot of the code was written by Jay and Ganesh. And so I'll just talk about 3 things that we care about for the H100. First is you want to use these new instructions. Warp group MMA for higher throughput. You want to use the TMA to do a lot of the memory loading. I won't go over the first one too much because it's conceptually straightforward. But the second one, asynchrony, I think is a lot more interesting. So this is a different way of thinking about programming, where you need to overlap the gem, the matrix multiply, and the softmax. And Hopper has great support for this. We were building on Cutlass 3, which has great support for asynchronous programming. And we had to use techniques like overlapping between different warp groups using warp specialization and ping pong, as well as intra-warp group overlapping, and I'll talk about what those means. And finally, I'll talk about low precision FP8. Okay, so new instruction. Okay, so the upshot is you can get about 1.6 to 3x speed up. It's the same algorithm, but a different way of programming, different instruction. There's usually, for example, in this particular case, we got up to 3x speed up compared to flash attention 2. So put another way, you can scale to 2 to 3x longer sequences for the same resource. Okay, so new instructions. Why do we care about these new instructions? For the A100, there's an instruction called MMA sync. In the H100, the instruction is called warp group MMA. And if you don't use this instruction, you can only reach about 2/3 of the peak throughput of the tensor core. So you really do want to use the new instruction if you're compute bound. The other thing is the TMA, which does memory loading for you. Essentially, instead of using each thread to do index calculation, there's a hardware unit that does the index calculation for you and saves a bunch of register. It also makes things more asynchronous, and that's helpful, as I'll talk about. Okay, so using the new instructions, relatively straightforward. Cutlass has great support for it. I think Pradeep has written like a 100-line example of implementing a matrix multiply on Hopper. So this is on Cutlass tutorial. So I highly recommend you guys checking that out. It's not that complicated, using warp group MMA and TMA, right? Okay, so once you've used the new instruction, you get most of the way there. But there are a bunch of things you can still optimize, one of which is exploiting asynchrony. So why do we care about asynchrony? It wasn't so much prevalent in Ampere, in A100, but for Hopper, you see a lot of the gem implementation, especially from Cutlass, exploit this asynchrony. So why asynchrony? So goes back to this old Amdahl's law, which says that the overall performance improvement by optimizing a single part of the system is limited by the fraction of time that improved part is actually used. So here's an example. So I won't go through the exact example, but if you work through the flash attention algorithm and you count how many flops you need to do for matrix multiply and how many flops you do for softmax, you see that the matrix multiply flops is way higher than the softmax flops, but the softmax requires this instruction called the exponential instruction. It uses this multifunction unit. And that multifunction unit is way slower, has much lower throughput. I think it's on the order of hundreds times lower throughput than the matrix multiply. So that means that you can make the multiply really fast, but you're still going to be bottlenecked by this exponential instruction. It's called exponential 2. So you can work out And for head dim 128, BF 16-bit, you see that the exponential actually takes half the number of cycles as matrix multiply. So most people just think of, only care about matrix multiply flops, but it turns out because the exponential unit is so much lower throughput, the exponential takes half the number of flops, of cycles. So that means that if you have to run these things sequentially, the tensor core, for a significant fraction of a time, is just sitting there waiting for the exponential function. And this gets even worse for lower precision, and this will get even worse for newer GPUs, where it's much easier to optimize to make the tensor cores go faster than some of these more complicated units like the exponential. So the answer is we need to do these things asynchronously. So the tensor cores are busy computing the matrix multiply while the exponential unit is busy computing exponential. Okay, so how do we actually do it? One easy way is just do nothing, and then the hardware and the software will take care of some of this for you. So there's a thing called the warp scheduler, that if one warp is busy doing, is stalled by something, it can switch to another warp and execute some other instruction. So this is an easy solution. It works okay, but you can do a little bit better. So here's an example of how you can actually kind of schedule the warp group. So here I'm having 2 warp groups. So each warp group is 128 threads. So these are on one SM on one thread block. And what you want to schedule is that while warp group 1 is doing softmax, you want to do warp group 2 to be doing matrix multiply, so that the tensor core is busy doing matrix multiply while the exponential unit is busy doing softmax. And you can schedule it in such a way that there's quite a bit of overlapping between the 2 warp groups. And the way you get there is using techniques like warp specialization and ping-pong scheduling. So you need to add some synchronization points to sort of force the warp scheduler to schedule it in such a way. And this gives you quite a bit of a boost, going from about 580 teraflops to 640 teraflops. Okay, so that's one way you can overlap. So now I'll talk about low precision. So why do we care about low precision? In theory, it gives you double twice the throughput essentially for free. So the hardware can execute, for example, FP8 matrix multiplication at twice the throughput compared to FP16. But there's a trade-off. Low precision means more numerical error. And there are ways you need to deal with that. Okay, so we need to borrow some techniques from the machine learning literature. Again, this is kind of a recurring theme where we are optimizing on the system side, but we're borrowing techniques from other fields like machine learning. So here's an example. If you can look at some of the features when you run LLMs, some of them have very, very large magnitude. And Tim Dettmers actually wrote an excellent paper called LM into 8 that sort of talked about this. Sort of, I think it was a kind of a landmark paper talking about outliers. So I highly recommend checking out that paper. It's called LLM into 8. And so how do we deal with these kind of features that have very large magnitude? If you just quantize naively, you suffer a lot of quantization error. So what you can do is you can sort of rotate everything by an orthogonal transformation and spread things out evenly. So here's kind of a little bit of math. I know it's early, so I won't do too much of this. So you take a random orthogonal matrix M. That means that M times M transpose is the identity. And you rotate the query. So you transform the query from Q to Q times M before you quantize. And then you do the same for K. And you see that because M is orthogonal, the dot product Q times K transpose is preserved. But because it's a random rotation, all the features are kind of spread out. And so you reduce numerical error here. In practice, we can use things like Hadamard transform, which is not a random orthogonal, but is a special class of orthogonal matrices that you can do the rotation in order of d log d instead of d square, where d is the head dimension. And this can be fused with things like rotary embedding, so that it costs you nothing to do this kind of rotation. Okay, so how does this work? So we think we get about 1.6 to 2x speed up. These numbers are a little bit, 1 or 2 months old. I think we've gotten quite a bit better numbers now. So with flash attention 3, we can reach up to for around 650 teraflops per second. So this is about 2x better than flash attention 2. Again, it's this same algorithm, but a different way to program. With head dimension 256, we can reach up to 750 teraflops. And this is essentially close to the speed of matrix multiply. Right? So now we have really, really powerful primitives. For a while, essentially, matrix multiply is essentially the fastest thing, and everything else was a lot slower. And now we have a really powerful primitive like attention that runs essentially as fast as matrix multiply on GPU. So that's pretty great. For FP8, we can reach up to 1.2 petaflops. I think most recently, we've been able to get to 1.3 petaflops. And we will continue optimizing FP8, especially for inference, now that a lot of inference workload are running on FP8. So with that, I'd like to summarize. So flash attention 3, this is a fast and accurate attention and optimized for modern hardware like Hopper. And we'll continue working on other hardware, AMD GPU, TPU. Blackwell is coming. I'm really excited for that. And 2 key ideas. One is asynchrony, and one is low precision. And the upshot is you can get faster training, better models with longer sequences. So with that, I'll stop here. Thanks so much for your attention.
Our next speaker today is a true AI full-stack capacity. Early on in her career, she designed the next generation GPUs at NVIDIA. Then she developed high-performance inference kernels and quantization kernels. And now she is an engineering manager at PyTorch, the PyTorch core performance team, where she is responsible for the latest and greatest PyTorch features and, of course, for the people behind this. So please join me in giving a warm welcome to Supriya Rao.
Thank you. Hey, folks, really excited to be here. Today, I'm going to be talking about quantization and sparsity, specifically through the lens of what we've been building for this at PyTorch. So we've been building this library called TorchAO, which stands for PyTorch Architecture Optimization, which is a library for quantization and sparsity that's easy to use, fast, and composable with the rest of the PyTorch ecosystem. So it works great with other PyTorch primitives like torch.compile and other distributed primitives like FSDP2. Instead of just being easy to use and build on, it also provides state-of-the-art performance for both LLMs and diffusion models on NVIDIA GPUs. So the main features that TorchAO provides are quantization and sparsity. Quantization enables you to run your model at a lower precision by quantizing your weights, activations, or gradients to different D types like int8, int4, FP8, NF4, etc. While sparsity works by removing parameters from your weights so that you can run your model faster during inference. And using these in PyTorch is a simple one-line API where you call the quantize or sparsify API, pass in your model, and pass in the specific technique you want to do. So there were a few symptoms that we observed in the open source community that really inspired us to create TorchAO. First is that getting a technique like quantization right is challenging. And even if you get it right, writing performance kernels for this is hard unless you're a CUDA expert. Moreover, once you get these techniques working, getting it to work with the rest of the PyTorch stack, like distributed training, is non-trivial. For example, let's say you want to run QLoRa with FSDP or FSDP2. Also, you have all these optimization techniques. There's always a question of how do these techniques compose with each other. And lastly, we all know and love torch compile and think it's amazing, but we don't know how to use it with these optimization techniques. And so our vision with TorchAO is that it should be trivial for you to quantize or sparsify any part of your model to whatever data type that you want, whether it's your activations, your gradients, or your weights. Run it for training or inference on a single GPU or 100 GPUs, all in native PyTorch, and all without sacrificing any performance. So how do we do this? In TorchAO, you can write your code in pure Python, and that gives you really fast development speed, and you can take advantage of torch compile to generate fast performant kernels. And you also get sort of like the composability support that you see in this diagram. In some cases, the compiler might not be performant enough. So we also provide ways for you to build, package, and ship custom Triton or CUDA kernels along with the library. So we think of ourselves as compile first, not compile fundamentalists. What this means is that we really build a tight feedback loop between Torch.io and the compiler, and we use Torch.io as a way to improve the performance of the compiler over time. So here's an overview of the quantization stack in Torch.io. At the very base layer, you have what we call the basic D types, and there are various signed, unsigned integers, and floating point D types that we provide support for. Sitting on top of these D types are the quantization ops and fast kernels. Quantization ops are operations that are used to convert tensors from low to high precision, while fast kernels are there in case the compiler may not generate optimized kernels. So now that we have these D types and associated operators, we can glue them together in an abstraction known as quantized tensor, and we have a support for affine quantized tensor, which is a subclass of a torch tensor type. At the top of the stack, we have the quantization flows, which is where most of our user-facing APIs live. So we have support for weight-only, static dynamic activation quantization, and various accuracy-preserving algorithms like GPTQ or HQQ. And the nice thing is that all of this is just in PyTorch without any external dependency. Under the hood, Torch.io uses tensor subclasses for most of its quantization flows. This provides a few benefits, the first being flexibility. So since it operates at a tensor level, we can quantize operations like functional linear layers, and we're not limited to just NN linear modules. Moreover, since it doesn't modify the graph, your model before and after quantization effectively looks the same. And this has an added benefit of making serialization and deserialization process really easy. So you can effectively load your quantized checkpoint into an unquantized model without requiring any prior transformation. All right, so this is how you would typically use quantization today in PyTorch or Torch.io. The first step when you want to quantize your model is to pick how you want to quantize it. And there are various parameters here that will influence your decision. First is whether your model is memory bandwidth bound or compute bound, depending on which you would choose weight only or weight plus dynamic activation quantization. Once you pick that, then you'd pick the D type that you want to quantize it to, depending on what your performance, hardware, or accuracy trade-off is. Once you pick these parameters, quantizing your model is just calling the quantize API with the specific technique that you want to quantize it to. This will give you an eager quantized model as an output, and if you want to make it go even faster, you can call torch compile on it to get even more performance. So what we noticed is that sometimes our users use our quantization APIs and their models actually run slower, which is not great. Why this happens is because quantization inherently has an overhead associated with it, and this overhead is amplified for layers with small shapes. So we built this tool called AutoQuant, which effectively leverages compile to generate micro benchmarks at a per kernel level and decide whether or not a layer should be quantized or what D type it should be quantized to. Another advantage of writing things in PyTorch is that these APIs are easily composable. We can take our int8 data type that we have and compose it with the sparse kernels to enable int8 quantization plus 2/4 sparsity to get even more speed up during inference. Okay, so let's look at some numbers here. This is Llama 3 at batch size 1, which is typically memory bandwidth bound. So a technique like weight-only quantization helps. And if you see on the chart on the left, as we reduce the precision of the weights, the speed up or the tokens per second increases, with the largest speed up being close to 2x for the int4 weight-only quantization compared to the bfloat16 baseline. Now we can also compose this int4 weight-only quantization with KV cache quantization and run the Llama 3 model with 128K context length in less than 24 gigs of VRAM on a consumer GPU. And writing KV cache quantization in PyTorch is just a few lines of code. This is written in less than 50 lines of code. And this is meant to be more as like a reference implementation that you can just copy-paste into your own model and enable KV cache quantization on it. On the training side, we also have easy-to-use APIs that enable you to do both computation as well as distributed communication in low precision, specifically for float 8, where we are seeing 1.5x speed up versus the compiled baseline. And under the hood, this uses a float 8 tensor, which is a tensor subclass type. And it leverages Torch compile to generate the fast floatate, scaling, and casting kernels, and also for fusing these kernels with preceding operators where applicable. With floatate training, you also get autograph support and distributed support, so it works with distributed primitives like FSDP2, tensor parallelism, and sequence parallelism. So inspired by bits and bytes, we wrote low-bit optimizers in PyTorch in a few hundred lines of Python code. So we have 4-bit and 8-bit optimizer support in Torch AO. And it's pretty good, like we see 35% VRAM reduction on the Llama 3 model with them. And the performance is also pretty good. Quantization works great, not just for LLMs, but it's also great for diffusion models. For some reason, my video is not playing, but it's a cute video of like a little baby astronaut hatching out of an egg on the moon. All right, so yeah, so for diffusion models, we saw like a 53% speed up with float8 quantization on H100s. This was generated by the Flux1 dev model. And for Coq video 5B model, for context, it takes like over 30 gigs to run it on the GPU. And with AutoQuant and compile, you can reduce not just the VRAM reduction by 50%, but you can also get like a 27% speed up because of compile. And as you can see, like these images were generated by quantized models, so the quality is pretty good as well. I want to give a shout out here to the Hugging Face diffusers team. They really like battle tested a lot of our quantization APIs and ran various benchmarks on diffusion models. So you should definitely check out their repo if you're interested here. So I spoke about a few techniques, but this is sort of like everything that we have today in Torch AO across inference, fine-tuning, and training. There's a lot more details like on the GitHub repo with benchmarks and API details. So if you're interested, basically feel free to check it out. The nice thing about Torch AO is that we've been able to experiment with a lot of interesting features in PyTorch. I want to call out a few here, which I think are really cool. The first is that Moby-Chem, who authored HQQ, actually added HQQ support in Torch AO in native PyTorch. So we not just have like fast kernels, we also have like good accuracy for those int4 kernels now in Torch AO. Vayuda wrote a lot of like low-bit int D-type support using tensor subclasses in Torch AO, which really like paved the way for us to invest more in low-precision inference now. Gonest has done some great work on int8 quantize and mixed precision training that's actually showing some pretty impressive results, which makes us want to invest more in this direction going forward. And Diogo integrated the 2-4 sparse Marlin kernels now into Torch AO, so you can see like even more improvement in the performance compared to the previous int4 weight-only quantization numbers I shared with you earlier. And like building on that, what we're really excited about next is the ability to run PyTorch quantized models on various backends. So a lot of what we've been developing on has been on NVIDIA GPUs, but for example, we'd love for us to be able to take quantized models and run them on your MacBooks or even on your phones. We've been like talking about a lot of D-types, but we don't really have a full understanding of how these D-types interact with each other, so mixed precision quantization is also interesting going forward. And building on the work on like float8 and int8 quantized training, we want to invest more in low precision quantized training, definitely. Yeah, on the kernel side, so far we've not seen great performant less than 4-bit kernels. The compiler-generated ones are not performant enough, so we're really looking for more feedback here on how should we think about writing these less than 4-bit CUDA or Triton kernels. All right, so, okay, there's a little hard there. Torch AO loves CUDA mode. Sorry about that. All right, so yeah, with Torch AO, we've been building all of these techniques as a community. Most notably with the CUDA mode community, which has been like a great way for our core team to get feedback on the features we build and really get a lot of interesting new contributions into the library. In fact, like some of the CUDA mode members are really core maintainers of the repo now. I want to give a shout out to a lot of folks from the server like Gonest, Vayuda, Coffee Vampire, Melvin, Andreas, Diogo, AIHD, Y4, and there are many more who've really helped us get to where we are today. And we're building this together as a community, and we really want to work with more of you going forward. So if you're interested in not building, but you want to try out Torch AO, you can also like pip install Torch AO. And we are also fortunate enough to be integrated into some other awesome libraries like Hugging Face transformers, diffusers, SGLang, and TorchTune. So you can also use Torch.io through one of these frameworks. Yeah, and lastly, I want to sort of like conclude by summarizing what we spoke about today. So I talked a lot about Torch.io, which is a PyTorch native library for quantization sparsity that's easy to use, fast, and composable with PyTorch. And really, this one thing I want to take away from this is that it's more than a library. It's like a community-driven project. And we really need more feedback from the community for the project to continue growing. And we've seeded a lot of like hacked ideas and projects together around the quantization, sparsity, and custom kernel space. So if you're interested in hacking on this, or if you want to make your first contribution in this space today, we'd love to help. So come find us. There are a lot of like core members of the team as well who are going to be wandering around here. And let's build some really cool optimizations together. Thank you.
So I'm now super thrilled to introduce to you a legendary person, someone who has been hacking and educating at the forefront of AI for over a decade. From neural networks to computer vision, from natural language processing to reinforcement learning, he has pushed the boundaries and inspired millions all over the world, including, I think, all of us here. He is a distinguished machine learning superstar, a founding member of OpenAI, the reference human for ImageNet, and an ex-Google Brain, ex-DeepMind, ex-Tesla, Mr. Autopilot. He has really seen it all. And some month ago, on a memorable day, this special person joined the CUDA Mode Discord to start hacking with others on LLM.c, which became one of the greatest and most active community projects on our server. But I guess it's best if he tells the story himself. So please join me in welcoming the incredible one and only Andrej Karpathy.
Wow, okay. Very impressive. Okay, yeah, I'm very excited to be here. This is my favorite kind of event to present at. So yeah, thank you for the invitation and thank you for running CUDA Mode and putting this on. This is like a wonderful event. Okay, so I'll tell you a bit about LLM.c. So what are we doing? We're training transformers in C and a pinch of C++. Okay, so I'd like to tell a story a little bit of how this project came about and what this looked like from my perspective. So roughly a year ago, I was trying to add a video to my YouTube series, and I was trying to teach people LLM training, GPT training, and so on. And I was basically hacking on NanoGPT trying to get it to work. So that was me. And then you've all worked with PyTorch, of course, right? So the trickiness comes that, okay, you have your model, which you've written, that makes sense. But now you have to keep track of a number of abstractions here at the same time. So you have to put it to a device, you want to compile it, you want to wrap it in DDP, and suddenly things start to get a little bit more complicated because I'm not even sure like in what order do you do these, what exactly happens, what are these abstractions, what do they do to your model? So I don't fully understand how any of this works. And then what happens is you want to use your model in different ways. So you want to use it in evaluation, in training, or model inference, and so on. And what happened to me is that I was able to train the model, but for some reason, eval and inference was not working. And what happened was I was getting some kind of a torch compiler when I was trying to run my eval and my inference. And this is just an illustrative example of a torch compile error. It was something else, I don't remember, I didn't capture it. But both of them were giving me error, inference and eval, and a different error, and I had no idea what was going on. So I did what anyone would do in my position. I went to short discuss. And I'm looking for PTR BLCK to solve my issue. Unfortunately, PTR BLCK did not have any guidance that I could see on that specific error. So I was kind of stuck, honestly. So 2 hours later of fighting with Torch Compile and trying to figure out what the hell was going on, I'm kind of a sad panda. I don't know exactly how to solve this. And so I felt like I was going through these stages of grief. In the beginning, I was in denial. I was like, this can't be happening to me. I'm not doing anything crazy. I'm just training a little GPT. Like, why is this not working? This seems really simple. I'm not doing anything crazy. And then eventually I entered the stage of anger. And I was like, okay, you know what? I'm just going to write the whole thing. Like, I understand in my mind what I'm trying to do. Like the computation itself, the algorithm itself is totally clear in my mind. And for some reason, Torch Compile doesn't let me like use it, run it, etc. So I felt a little bit powerless, and I was like, okay, I'm going to take life into my own hands and be in control of my destiny. I'm going to just write this in C. How bad could it be? So let's think about like what is PyTorch offering you really? And there's many things, but maybe some of the things that are relevant here. I don't know why those bullet points are 111. I don't know what, on my slides it's totally fine, so I don't know what conversion happened here. Okay, but number one, we're getting an array, right? So a very useful n-dimensional array that we can manipulate the operations. If we're gonna abandon this, then we're gonna have to do a lot of pointer arithmetic, basically, making sure that we ravel and unravel indices correctly. Second, we're getting autograd for free. So if we don't have autograd, we need to do forward and backward passes of all the layers. We don't have device, so we have to worry about memory being on the host or on the device and shuttling memory around your different devices between CPU and GPU and so on. We don't have simple D-type conversions, so we have to be very mindful what tensors are stored in what precisions and convert explicitly between them. We don't have Torch Compile, so we're going to have to do all the kernel fusions that we want manually, and we're going to have to optimize for space and time performance manually. And finally, we don't have distributed, so we're going to have to manually spin up all of our processes, make sure that they can find each other, communicate with Nickel, etc. So PyTorch is really, really nice, and this is just some of the things that PyTorch offers. So without PyTorch, we're kind of naked in the world, right? But maybe it's okay. So yeah, how bad could it be? So step one, we have our PyTorch code, which now isn't the primary thing we're working with. It's only a reference that we check correctness with respect to. And so we're in PyTorch land, everything is nice and clean. We have a little transformer, a few modules, and we're just calling them, so everything is great. And that now becomes our reference in PyTorch. I'd like to just take you through one example of a layer. So for example, layer norm here is like a PyTorch layer. And we'd like to basically port this over to C. So what kind of process do we go through? Well, we're going to iterate through all the layers. Number one, we need the forward pass. And actually, I had to write a forward pass of layer norm because PyTorch doesn't just have this kind of implementation in PyTorch of layer norm because it's kind of like a block and eventually it calls into some CUDA kernels. So I had to write the forward pass of layer norm and make sure it's equivalent to the layer norm in PyTorch. And then, of course, I had to write the backward pass of layer norm. This is where you kind of take out your pen and paper, do some backprop. This is for batch norm, but layer norm would be similar. And yeah, we have to write the backward pass. And again, this is all still in PyTorch, but it's explicit, and you're just making sure that layer norm of PyTorch, forward and backward, matches this basically manual tensor-based implementation. So now we have PyTorch code forward, backward. So next thing we do is we try to port it to C. And this is actually like a lot simpler in many cases than you might think. So on the left we have the PyTorch code, and on the right we basically have the equivalent layer norm forward in C. And it's not that crazy, right? So unlike in PyTorch, we just have a bunch of float star arrays. So we have a float star out, float star inputs, outputs, means, standard deviations, weights, and biases, and some hyperparameters. And one thing I really liked to do in LM.C is I just want to keep things simple. I don't want to create a tensor abstraction. I don't want to create any abstraction, really. It's just float arrays and operations on float arrays. Like, why should it be a lot more complicated than that? So everything is just float arrays. Everything is fully self-contained. There's no underlying representations, abstractions to call, import, etc. This is the layer norm forward on float arrays, and that's it. So that's the forward. And then you also do the backward for all the layers. Once we've done that for all the layers and converted everything to C and made sure that everything matches our reference implementation, we have to start to string it together. So we go into our C code int main, and we have to allocate all of the memory that we're going to be using. In LLM.C, all of the allocation happens a single time at the beginning. So we pre-plan all of the memory that we're going to ever use. Then it's fixed, and from then on, it's just dynamics of just feeding data through it and training the model. So we have to pre-plan all of the tensors, their sizes, and we have to do that for the parameters, and we have the data grad and the MNV for the AtomW buffers, and then for the activations as well, and we need space for both data and grad. And so you just pre-plan all of the memory, you allocate all of it, and then we need to stitch it all up. So we have all of these layers, and they have a forward and a backward pass in backpropagation. And so on the forward pass, just kind of like you allocate all these tensors and you're very careful and you index into them properly and you make sure everything flows correctly through. And you just call all the forwards and then all the backwards, and then you're kind of done and you're left with gradient and you can do an update. So stringing that together is the second piece of work. And then once we sort of like strung it together, you get something that you can just compile and run. So on the top left is everything that's required. We download a starter pack, which is really just the GPT-2 weights in a single binary file, very simple. And also we need the data set, in this case Tiny Shakespeare, and the tokenizer and stuff like that. And then we just compile and run this little C code file. It's a single file of C at this point. And I think it's like 2,000 lines or something like that, if I remember correctly. And you run that program, and it like does a little training and outputs some Shakespeare at the end. And then we can verify that the PyTorch code is identical to the C code, and everything is great, and we're just running in C. And at this point, I'm actually feeling quite great, because this is amazing. So we have a single file of C. There's no dependencies whatsoever. It compiles instantly. It runs instantly. All of the memory is just allocated in a single blob. So if you start stepping, there's no way you're going to later. It's all pre-planned. It's fully deterministic. It, in principle, can train GPT-2. It's complete. It will train GPT-2. You just have to wait a long time. And it can run on a potato. It can just run on anything. It's just a single file of C with no dependencies. And in principle, this would be a great candidate to run on a von Neumann probe, because in space, if we just harden it a little bit more, because you're not going to ship PyTorch code on a von Neumann probe, but I think LMC is a great candidate for that. So I was feeling great at this point. Fun side note, by the way, all of this work that I described so far happened on a vacation while I was jet lagged in Maldives. Basically it's perfect because you wake up at 1 a.m. and there's nothing to do. So you write stuff like LLM.c, and then in sunrise you go do all the weather activities. So that is the villa where most of LLM.c was trained. So that was perfect. This is a picture of it. And this is I think the moon is about to set and the sunrise is about to happen. This is a recommended way to do software development. Okay, so now we have C code, but it's inefficient. So we'd like to run it faster. For that, we reach for GPUs. So we need to convert all of our C code to GPU. So this is where we go to the dev CUDA part of the repo, and we start to develop all the kernels. So here's the layer known forward pass, as I mentioned. And now we're going to develop a number of kernels that have the identical functionality, but now run on the GPU, and they're going to be faster. And so usually we have versions 1, 2, 3, 4, 5, 6, etc. And these are all different kernel implementations. They're a bit faster usually over time, but they match the specification exactly and give the exact same numbers. So we develop all those layers, import them to CUDA. And this is, I don't know what this is. I'm going to skip that. It's like one of the kernels. Basically, the point here is the first kernel is trivial to do usually because you're parallelizing over batch and time, and then you're basically copy-pasting the C code into your CUDA kernel. And you're already getting speedups because you're parallelizing over the batch time tokens, and each thread just handles a single output element. So the first kernel is usually trivial, but then optimizations can be pretty elaborate. So by the end, we get to kernel 6, for example, in layer norm, and we're doing a lot of things that are a bit more complicated. So we have some, warp-reduce operations. We have some. We also communicate through shared memory, through global memory. We're orchestrating it correctly. Cache streaming hints and a bunch of little tips and tricks for dealing with everything. And I'm going to go into a bit more detail later. But you can get arbitrarily complicated here writing the CUDA code. One thing that I sort of found in this project is that it's not exactly trivial to learn CUDA, unfortunately, and it was like a little bit harder than I expected. I knew some CUDA going in, but getting better at it, I think, is not trivial. I think some of these books, unfortunately, are a bit out of date, as you might know. PMPP is actually quite good, but also, I think, still kind of like mostly on the beginner level, because a lot of the CUDA code that we ended up developing in the lifetime of the LMC project, you would not find those things in this book, actually. So a lot of the kernels that we ended up adding would just not be covered. And then on top of that, you have this CUDA C++ programming guide, which frankly is not exactly readable for someone who is like a bit new to that, to CUDA. And then you have this amazing blog post from Simon, who's at Anthropic, that is like way better than anything we deserve, just like randomly on the internet. So that was incredible. And if there was just more of that, that would be so amazing. But yeah, so I think I found it a little bit difficult. But I mean, I'm hoping that things like CUDA mode can definitely speed up the availability of writing CUDA. Okay, so next what happened is I was basically struggling with the CUDA code a little bit, and I was reading through the book, and I was implementing all these CUDA kernels, and they're like okay CUDA kernels, but they're not great. And so a team of Avengers assembled from the internet when they saw LLM.C and started contributing. So specifically, Eric, Arun, Alexa are kind of like, I would say, core devs of LLM.C and have contributed a ton of work to LLM.C. And they started to like really optimize and write all these kernels, and this was incredible to watch and learn a lot from. And there's many more, Ross Wheeler and Chinthesol and a few others. Over time, we have 60 contributors to the LLM.C project. Shout out to Lambda for sponsoring LLM.C. They contribute compute so that we can run and optimize all these kernels. So it was amazing for me that people just came from the internet and helped out on the project. And this is one of the favorite things that can happen. My favorite things that can happen with an open source MIT licensed repo. People just come from the internet and help contribute. It's amazing. Okay, so we've converted all the layers to CUDA. We have now all the kernels, and we can now train on a single GPU in FP32 so far. So that's great. So from then on, we start to make more and more optimizations. So number one, we don't want to have matmults in FP32 when you roll your own code. We actually switch to cuBLAS. Step two, we don't want to write our own flash attention. I think that would be pretty complicated. Turns out cuDNN has a very good flash attention implementation, so we switched to that. Next, you want to definitely reach for mixed precision so that to speed up the code. So you want to go over all your tensors for parameters and also for activations and so on. And you have to start to think about, okay, which ones are in float 32, which ones are in bfloat 16, and what precision are they in, and then do all the conversions automatically. So we reached for that and implemented that. There's many, many other optimizations that we ended up implementing over time. So as an example, we did all the kernel fusions, different recompute settings to recompute a piece of the forward pass during the backward. There's been a lot of optimizations from Eric especially on minimizing the amount of memory that you need during the backward pass. We have this like packed 128 data structure, which basically, in our experience, forces the compiler to use the 128-bit load and store instructions that are available, but somehow the compiler is unwilling to use in many cases. So I think Arun did a lot of work here where you just look at the SAS and you look at the SAS is the assembly, and you are looking at what instructions are being used for your loop, and you figure out that, okay, this should be a 128-bit load and store, but happens to be a 32-bit or something else because something in the MVCC compiler is not going very well. So we found that this data structure kind of forces the compiler's hand a bit more. We implemented all kinds of CUDA streams to overlap the part of the computation, and this ended up creating like a total disaster. And so that's why I scratched it out, because at one point of LLM.C, as Arun would say, I basically went in and I nuked it from orbit. I just went in and I Control F for all mentions of stream, and I just delete. And basically I deleted all the streams, made everything single-threaded, because we ended up getting all kinds of really weird race conditions and errors and so on, and I just didn't want to deal with it. So LLM.C is not actually as overlapped as it could be, but it's just like, it's too much complexity for not enough gain at this point. So, but maybe we can slowly reintroduce some of it. We have stochastic rounding, we have full determinism. Full determinism turns out to be pretty hard because some of the kernels complexify a lot because you can't use atomics. Like the encoder backward was especially crazy because encoder backward is trivial with atomics, but non-trivial without it. Anyway, so a lot of the optimizations went into with a lot of efficiency and determinism in mind. And accuracy, like stochastic rounding and so on. Next, you want to use multiple GPUs, not just a single GPU. So this is where you bring in nickel. You start to do all reduce between all the different workers. And this is where you also start to reach for like sharded optimizer state 0, 1, where basically you take your optimizer states, which are in float, and these are really large buffers for atom W, and you can actually spread out a lot of this stuff across all the GPUs, and it really helps to keep your requirements down per GPU in terms of memory. So very helpful to reach for that. So currently LLM.C uses 0, 1, which is a sharded optimizer state. There's a PR for 0, 2, but I don't believe I merged that yet because it gets a little bit messy, but might be merged eventually. A lot of LLMC is just kind of like balancing the improvement in speed with the complexity of what you're actually introducing. And so I've actually rejected a lot of PRs because of that, because the code starts to get crazy. And I think that decreases the amount of people that can be onboarded into the project. And then after multi-GPU, you have multi-node. So now you are running across multiple machines. You have to make sure that you synchronize all of them, that they can find each other and so on. So we implemented all of that. And where that leads us to is that we can actually train GPT-2, and we can actually reproduce it after all of that work. So there's a post in the discussions of LLM.C. We can train the 1.6 billion GPT-2, which was state-of-the-art LLM as of 2019 or so. And you can train it on a single node of H100s in about 24 hours, and that costs roughly $600. And the way you do that is it's extremely dependency-free. There's no need for Python, no need for PyTorch. You do need cuDNN, which is the most heavy dependency, but cuDNN is optional. So if you'd like to roll your own manual attention, that is possible in LLM.C. But cuDNN is kind of like the hairiest dependency. But after that, it's just a bunch of C code. You compile it and you run it. There's no need for really anything. So there's no need for conda environments, pip installs. There's just nothing, which is amazing. And then you compile your code, then you run it, and it starts stepping. You wait 24 hours. And then it's stepping. Print some diagnostics. We have almost 50% MFU here on one node, which is quite good. And you get really nice plots, and you beat GPT-2 on HellaSwag. And basically, this just indicates that the optimization went well. No crazy numerical issues, lost spikes, or anything like that for this size. And yeah, achieving a really good model in LLM.C. We can still compare to PyTorch because remember, we have PyTorch implementation for all of this stuff in parallel on the side. And so you can run the equivalent training loop almost in PyTorch, and we can compare the two implementations side by side. And in particular, at the time of writing that post, and I don't know if this has changed because the PyTorch team continues to optimize things over time, but at the time of that post, we were using in LLM.C 30% less memory, and we were 20% faster in training, just the throughput. And I don't know if I fully super duper optimized the PyTorch implementation. I did my personal best, but we were able to, I think, beat PyTorch in training of specifically GPT-2 in LLM.C. If you want to train anything else, you're in a lot of trouble. But you have to change your code a lot, and we're doing that, and I'll come back to it. But for GPT-2 training, we're better after all that work. And it also compiles and runs much faster, which is beautiful. Torch compile actually takes like quite a bit of time, like a minute or something. You're just waiting. So that's also something that I personally don't like to work with usually. OK, so looping back around, turns out it wasn't all that simple. There was a lot of stuff involved, and it took a few months for a few people. But it was fun. We learned a lot, and we made friends along the way. This is the LLM.C core devs. So it was great. Ongoing work. We are adding Llama 3 support. We actually thought maybe we would have it done by today, but there's a little bit more work to do. But we will have Llama 3.1 training in LLM.C very, very soon. We will have FP8 support. So Arun has been working on this, and there's a big PR that's coming for FP8 support, which is also interesting. And there's a lot of notable forks of LLM.C. They're all listed on the GitHub repo. The AMD fork is very active, as far as I understand, and quite good. I think also the C++ CUDA fork is quite nice. And so a lot of forks. So encourage you to also fork LLM.C. It's fairly readable, I think. I tried to keep it clean, well documented. I think it's pretty well understood what's in there. It's only maybe like, I think, 3,000 lines of code of basically C mostly. And one more thought I think that I wanted to get across is it wasn't all that haphazard to start the project. I had another motivation for starting the project. And that's that I think, what is LLM.C? Like if PyTorch is, especially Torch compile, is a bit like GCC for software 2.0, it's a compiler, then LLM.C is a bit like writing assembly. We're doing everything manually, right? And basically I think we wrote LLM.C as multiple people over a duration of 3 months and got something that was faster than PyTorch in a specific setting of GPT-2 training. And so what this exercise basically proves that this is possible. Now, the problem is you need to spend multiple people several months. But if LLMs are about to become much better at coding over time, then I think you can expect that the LLM could actually do this for any custom application over time. And so the LLMs could act as a kind of compiler. For any custom application you're interested in, they're going to do all the LLM-C work, and they're going to output a binary that you can compile and run for your specific applications. So I don't actually know if the use of Python and PyTorch and everything else is just a crutch because we humans are finite. We have finite knowledge, intelligence, and attention. But actually, don't you want to write all code in custom CUDA kernels and so on? Like, maybe. And so the other thing that I think is interesting is the LLM.C repo might be useful because in the early stages of these LLMs and their intelligence, they might not be able to write this code from scratch. If you just prompted them write GPT-2 and C, you probably won't get LLM.C. But you're a lot more likely to get it if you put LLM.C in the context of such an LLM, and you can expect that the few-shot learning would be very helpful for the LLM to basically give it example code. And so I think LLM.C could be very useful for this example code to give to the LLMs as they're about to write all of our custom applications. And so I think this is actually not unlikely to happen. yeah, this is kind of likely to happen. So I think software development in general will probably change a lot. And to me, LM.C is an exploration of whether this is even possible. Because if it is possible, then maybe this is what's going to happen. So yeah, that's it. Thank you.
So our first talk will be given by a brilliant PhD student from UC Berkeley, who is a core developer of the VLLM project, which is one of the most used high-performance open-source LLM inference engines out there, with dynamic batching, page detention, custom kernels, speculative decoding, quantization, and many other features. They together with their, she together with their incredible team have been pushing the boundaries of what's possible in open source and available in terms of inference speed and efficiency. Always minimizing latency and maximizing throughput. Please give a warm welcome to Lily Lu.
Thank you, thank you. Hi everyone, I'm Lily. I'm currently a PhD student from UC Berkeley. So it's a great honor to represent the VLM team to talk about our project in CUDA mode. It's a great event, and other team members of VLM is actually also here, like Kai Chao, Usuk. Feel free to catch up with them like if you get time. Okay, so let me get started. Okay, so for this talk, it will mainly have 3 topics. First, I will introduce VLM project. And next, I will highlight 2 features, like 2 new features in VLM. The first one is torch compile. The second one is speculative decoding. So the goal of the VLM project is to build the fastest and easier to use open source LM inference and serving engine. So we launched the project in June 2023, and when there were only very few like open source projects for LM serving. And we are very lucky because we get lots of traction from the beginning, and it has become one of the most popular projects in this field. And we have lots of like users, industry users, including like those big cloud companies like Google, AWS, or Azure. So why do people use VLM? I think one of the reasons is that VLM has very easy to use APIs. So we have the LM class, and the user just need to specify the prompts and the model they want to use, and then it just call the .generate function on those prompts. And under the hood, the VLM will handle the scheduling, handle the KV cache management, do the request batching automatically. So user does not need to worry about those things. So we also we also support VLM as an OpenAI API compatible server. So the users can just serve the VLM, use like VLM serve, and specify the model you want to serve. And then you can just use the OpenAI client, send the request to the endpoint. You just replace the URL with the local URL. Another strength of VLM is very broad model support. So VLM currently support almost all the popular like OpenLLMs and VLMs. So we are the official launch partner of Llama. So we support Llama new models from day 1. And we are also have very close collaboration with those like state-of-art vision language model creators. Like for example, Pixtral and Qwen, like they contribute their like new vision language models to VLM. On top of that, I think VLM also supports many features. Right? First, we support various like quantization methods, including like FP8, GPTQ, AWQ. We also have the LM compressor so that the users can compress their models, use different like compression methods. So VLM also support like prefix caching. So this can be an important feature if like lots of prompts, they share the same like system prompt. So in that case, we can reuse the KV cache of their input, of those system prompts. So we also support like pipeline parallelism. So pipeline parallelism is important when the model is too big to fit in a single node. or you want to serve like models with some PCIe connected instance such as L4. And lastly, we also support like multi-LoRa serving. So you can serve multiple LoRa adapters in VLM. We can load those adapters to the GPU memory dynamically. So actually, we provide like many more features like besides what I mentioned before. So in today's talk, I will dive into a little bit about torch compile and speculative decoding. But we also have like trunk prefill, guided decoding, KV cache offloading. So I encourage you to take a try if you are interested. So of course, VLM is built for performance and efficiency. So in LM serving, there are 5 types of kernels you might want to like implement your custom kernels instead of writing pure PyTorch, right? So here VLM supports like different types of kernels. So for example, for the quantized gem, we find Catalyst kernels provide the best performance. And for group gem, we find that Triton is more beneficial in that case. So we use the Triton kernels for those group gen, and they are used in the MOE serving in VLM. We also have like a custom or reduced kernel for small batch size in VLM, because we find that Nico's ring or reduce is not very good in those small batch size scenarios. We also have different like attention backend, right? Like flash attention, flashing for OX formers. So for all those kernels, we all use like CUDA graph to minimize host overheads. But building an inference engine is much more than just write kernels. Like in the process of building VLM, we learn a tough but valuable lesson. So we learn that to fully utilize the GPU, we need to pay close attention to everything happening on the CPU. GPUs are fast, but CPUs are not. So LLM's inference engine is doing much more than just running the model, right? We do like tokenization, detokenization, scheduling, memory management. All those logic happens on CPU, and in VLM, it happens in Python, right? So which are might be even slower. So if they are not handled correctly, they might become the performance bottleneck. And that is what we have experienced. So VLM is currently undergoing some rearch, and we also have lots of like multi-step scheduling, asynchronous output processing to reduce those overhead. So I encourage you to check out our recent blog post. So we do hope that VLM is not only feature rich, but also become very performant. So lastly, I want to highlight that VLM is a community project. So we are joining the Linux Foundation, and we are hosting like regular meetups and office hours with our collaborators and users. Next, I want to talk a little bit more about Torch Compile. Let's dive into it. So I think since the start of the Torch Compile, VLM is very actively integrating this feature. But we find that since VLM is a big project, you cannot just write a Torch.compile, a single line of code to do the integration. So we actually divide our integration plan into 4 steps. So let's go over them one by one. So the very first way we integrate Torch Compile is to apply it locally. So for example, models often have have slightly different layer norms in terms of like precision or operation order. So instead of developing a custom kernel for each layer norm, we just use Torch Compile for those slightly different like layer norms, and treating it like a Triton kernel generation. So this is already a big win for us because we don't need to write any kernels ourselves. We just use Torch Compile. However, to unlock more optimizations, we want to apply Torch Compile more broadly. So the second step is we want to use Torch Dynamo to capture the full model. So in the second step, we capture the entire model But the challenge there is that we need to register every customer operations in a way that Dynamo could process. So we want to avoid unnecessary like recompilation. And we also have some special handles for those like in-place custom ops. Next, we are enabling torch inductor to optimize those captured graph. So we hope that with the torch inductor, we can optimize the performance using some Trident kernels for those small gems. And it can do the operation fusion more aggressively and do more like efficient memory planning. So looking ahead, in Q4, we want to explore further optimizations with torch compile. So for example, we want to add some custom compiler passes for new types of operation fusion, like fusing the epilogues, prologues of the quantized kernels. So please stay tuned for this one. So lastly, we want to highlight that VLM is a multi-hardware platform. So currently, we support like 4 different types of hardware, include different types of different GPUs, CPUs, and custom AI chips. So, and this is possible because of the we rely on like we have a very close integration with like PyTorch. So instead of relying on some like external compilers or formats like Onyx, we just use PyTorch as a narrow waist. So it's a middle ground to connect different backends with hardware agnostic models and utilities. Okay, so for the last part, I will just go through another feature currently we are actively working on in VLM, which is speculative decoding. So before I dive into the feature, let me give you a recap, like what is speculative decoding. So we think it's an important feature because it's a feature to help reduce the LLM inference latency. So the intuition is that like some tokens are easier to generate than the others. So instead of using the large language model to generate all the tokens, we use some small model to like propose tokens to generate the easy tokens and the large model to generate difficult ones. So to give you a more concrete example, so like here, given a prompt, we will generate the, like without speculative decoding, we generate a token one by one, auto-regressively. But with speculative decoding, we will send the prompt into a small model first, and the small model will propose token auto-regressively. It will say, oh, the output might be T1, T2, T3 prime, and then it will send those tokens for the large model for verification. So the large model will verify the correctness of those proposed tokens. So in the example here, right, a single forward pass of the large model generates like more than one token. It says T1, T2 is correct, T3 prime is incorrect. So in a single forward pass of the large model, we generate more than one token. This reduces the like token generation latency compared to the like one token per forward pass. And the VLM is a system that natively supports continuous batching. So how does speculative decoding work with continuous batching? So actually, it's pretty simple. So we will have a draft runner which can propose token like auto-regressively. The draft runner is responsible for running those small model. And then we will send it to the target runner, which will run the large model for verification. So the large model will tell us, oh, which token is correct, which token is incorrect. It will also generate some like bonus token. Basically tells us, oh, if it will correct the last incorrect token or generate one extra token if all the proposed tokens are correct. And in the next iteration, we will resume from the bonus token. So to implement speculative decoding in VLM, we change the scheduler so that the scheduler can schedule more than one memory slot for each request. We also change the memory management to manage the KV cache for both the small model and the large model. And the speculative decoding worker is responsible for like calling the draft worker to propose tokens, the target worker to verify like which tokens are correct, which tokens are incorrect, and also the rejection sampler is responsible to generate the final output. So we try to make the framework as general as possible. So we have different flavors of like speculative decoding, which I will dive into in the next slide. So the most standard speculative decoding we have is a draft model-based speculative decoding. Basically, we use a small model to speculate the large model. And there are some commonly seen model pairs, like Llama 68M to speculate 7B model, 7B model to speculate a 70B model. But one challenge in this case is, like, how do you find a good draft model? So to be very honest, we haven't found a good draft model for a 8B for Llama 3 8B. So we could not use the Llama 2 small model like for the Llama 3 because they have different vocabulary size, and speculative decoding requires that they have the same vocabulary. So that's why in VLM we also support like draft model free speculation methods. So the first type of draft model free speculative decoding we support is prompt lookup decoding. So prompt lookup decoding, let me give you a very quick example. So given the prompt, like what is the capital of South Korea, we will generate all the possible 2 grams and all the tokens, all the tokens that follow the 2 gram, right? Like the token after what is the capital of. So during the generation phase, when we see the 2 gram, like when we see the capital, we look up it in the lookup table, and if we find a match, we will just propose the tokens based on the value we store in the lookup table. So like the example here, we find, oh, the of South Korea might be the following tokens, and luckily they are all guessed correctly. So in that case, in a single forward pass, we generate 3 tokens. So prompt lookup decoding works pretty well for those like summarization, question answering data set, where like the output has a big overlap with the input. We also support like other like Medusa, Eagle, MLP speculator, like those type of speculation methods. So instead of using a small model, they have some additional layers or additional heads to propose tokens. So what's the performance? How good is speculative decoding it is? So we benchmark those methods, and the first one is draft model-based speculative decoding. So the blue bar is with speculative decoding, the red bar is original, like without any, without speculative decoding. We find that it can improve the performance, like bring up to 1.5x speed up at QPS1. We also benchmark those n-gram speculative decoding method, and we find that it can bring up to 2.8x speed up when the QPS is small. But that's not the end of story. So during the integration of speculative decoding, we find that sometimes when the QPS is high, it can actually slow down the performance. So this is a full picture actually. So when the QPS is like say 10, we find that it brings like 1.4x slowdown, 1.x slowdown on the 2 data sets. So it tells us that speculative decoding is not always beneficial. So let me give you some intuition behind the slowdown. So in the example here, we have 3 requests, and we propose 2 tokens for each request. So there are in total like 9 input tokens. And after the verification, we find that only 1 of them is correct, and we generated 4 tokens, including the bonus token, with computing 9 tokens. So we are wasting 5 tokens here. We are wasting some compute here. So this type of waste is fine because we know when QPS is low, LLM inference is memory bound. But when the QPS is high, it becomes compute bound, and such waste can be very expensive. And instead of doing speculative decoding, you might just want to do normal decoding. In that case, you are generating 9 tokens with computing 9 tokens. You don't waste any compute here. So this motivates some like ongoing research within VLM. So we propose some like dynamic speculative decoding. It can dynamically adjust the proposed length based on the system load and speculation accuracy. So we are doing like even step level, different generation steps have different proposed lengths, or even request level. So on the high level, it's just when the system load is high, we do less speculation, and when the acceptance rate is high, we kind of do a little bit more speculation. But I encourage you to check our paper for detail if you are interested. But the goal here is we really want to enable the speculative decoding feature in production. So basically it means it should always improve the performance instead of degrading the performance. And to use it in VLM, you just need to specify what's a speculative model you want to use and what are the number of tokens you want to use. And similarly, like for n-gram, you just change the speculative model into n-gram. Okay, we talk a lot about speculative coding. I think now let me give you a summary. So I think VLM is a popular LLM inference engine with broad model support and rich features. It leverages torch compile to ensure high performance, and it efficiently supports various speculative decoding methods. So we really hope and we are really grateful for the community to contribute so much and so many users to use VLM, report the issues, and we are actively working on this project to, we hope it can be better in the future. Thanks for listening, that's all.
As our next speaker today, we have nobody less than the actual inventor of CUDA mode, the fabulous Tim Dettmers. So during his NeurIPS presentation last year, he described going into CUDA mode as working in highly efficient flow state, basically forgetting time and space and becoming one with the code. Tim is not only an exceptionally good researcher and incoming assistant professor at CMU, but also an open source superhero who's relentlessly fighting for the GPU poor with his high quality open source quantization and sparsity contributions, making deep learning accessible for everyone with production quality libraries like Bits and Bytes, for example. It is an absolute honor to have Tim here with us today. So let's give him a warm welcome, Tim Dettmers.
Thank you so much, Andreas. So whenever I give a talk like this, I try to come up with something new you can't find online. And so today I want to talk about competitiveness in open source. And so this is a little bit maybe unusual sort of in the open source space. In the open source, we want to collaborate. We want to build on each other's work. We don't want to compete. But I'm also a researcher, and for me, I'm thinking about the future. And the worst thing you can do in research is work really, really hard on a problem that doesn't matter. And the same in open source. One thing that's not very productive is you work really, really hard on a feature that becomes obsolete. So that's why it's sort of also important to think about the future. And often when I think about the future, I think about how can be something competitive. And if you think about back how open source was before this, Stable Diffusion, it was not much going on. When Stable Diffusion happened, everything exploded. It was this Cambrian explosion of collaborations, new projects. Every day you went on Twitter, like Stable Diffusion got faster and faster, and it was exciting. And everybody knew it was just a matter of time until this happens. Llama models. And then also the large language models exploded dramatically. And so that is what competitiveness looks like. If we can compete with closed source, we have this explosion of open source models and the entire ecosystem. It's a very rich environment. But when we look forward, we probably will not see GPT-5 level models open source. They're just too expensive. And so we need to think about what will happen then. How can we compete then? We don't want to be obsolete, but in open source we have strengths, and we can use these strengths to our advantage. And so I want to talk a little bit about different scenarios, and here I take a perspective from how can you view our competitiveness from the perspective of open source. And I think there are three different scenarios. If everything works well for open source, they solve all the problems and they're very cheap to use, and everybody will use closed source solutions. And I will talk a little bit about what we can do in that scenario. Another scenario is there's closed source and it works really well, but it's really expensive. So that's an opportunity for the GPU poor to band together. And then the third scenario is where open source sort of wins closed source, doesn't quite work. GPT-5 level models cannot produce end-to-end automation, everything gets messy, and it might also be just too expensive to go further than that. GPT-6 level models will be expensive. So let's talk about some of the details here. Closed source works and is cheap. If you look at that future, it basically looks like everybody will use the closed source APIs. That's the tool of choice. How can we compete in that environment? So if we think about the competitiveness factors, one is sort of still privacy. There will be a lot of people that still say, I will not send my data to this API. Be it hospitals or other sort of very privacy-focused institutions, but it might be also just users, like my personal data. Oh, I will not send it to some OpenAI API or something like that. Maybe you want to process on your laptop, and that is a competitive advantage. So thinking about that, how can we make privacy a strength? Then also latency. There are physical laws. The coast-to-coast latency is 70 milliseconds, so the round trip is 150 milliseconds. Some applications are latency critical. It might be sort of voice, but then also, for example, if you have tool use and the in-between tool use latency is low because the tool executes quickly and the language model quickly knows which next tool to call, you have a chain where latency becomes really important. And so for some agent system where tool use is really important, these might be better served on a sort of a local device that's close to where you actually make the API calls. So an API in the cloud might be too slow for that. That might be a competitive advantage. Then also the entire ecosystem. If you think about companies, they need to focus. They can't do everything. It's just too much. But we in open source, we can focus on all kinds of different aspects just by sort of separating it in different groups and then come together to build an ecosystem that's very rich. Another competitive factor. So even if closed source is a tool of choice, we can compete by thinking about these competitive factors. Let's talk about closed source if it works, but it is expensive. This is the opportunity for the GPU poor because only the GPU rich or and generally rich companies and consumers will be able to use these APIs. So they use then these very expensive GPT-5 level or GPT-6 level APIs, but they pay a lot for that. In that scenario, the sort of cheapest choice is always to use devices that you already have. And so I talked about privacy, and their laptops might be an advantage. But here it's also a laptop. You already own laptops. A lot of MacBooks, and these MacBooks are pretty good to run AI models. And you might think in the future we have these big models. Laptops can't run them. But think about O1. O1 is mostly inference. You can get benefits like this from a small model that you run for a longer time on a laptop. I think it's very much possible. There might be also sort of mobile devices in an equation here, but it's also a question, what do we do with these AI models? It's not quite clear. And I think, if I think most use cases, they're still very useful on laptops, but the question is, what do you do on mobile devices with AI? I think it's not quite clear, but it might be an important factor where open source plays a role. Another thing, and that is sort of what I did with QLoRa, if I tell companies, hey, I have this method, and now we can fine-tune by using less GPUs, they say like, okay, I just use more GPUs. Why would I use this? I already have enough GPUs. And so this is really a feature that's really good for the GPU poor, but the rich say, like, I don't want to take any risk and have a quantization. I've trained in full precision on my GPUs. And so if we create features that are designed for the GPU poor, that's a big advantage for us, and that's how we can change sort of communities. So just thinking about if you have a limited compute scenario, if you have a limited memory scenario, how would you change your approach? That can be helpful to think about that. And then often we think about efficiency if things are too expensive. But it's also the case if things are too expensive, then people need to use open source. They cannot use the APIs because they're too expensive. And then one of the most important factors is just how easy is it to use the things out there. And bits and bytes, I think a factor for its success was that it's so easy to use. You can just say load in 4-bit and you got the model in 4-bit. And thinking out about how you can build tools that are very easy to use, I think that's a competitive advantage here. Okay, let's talk about the scenario where basically open source wins. Closed models are not good enough, end-to-end automation will not work, and it's also really expensive to continue. And so I think that is actually a very challenging scenario for open source, because this is a scenario where open source needs to lead. And if you look at other companies like OpenAI, they try really hard to land products that people like, but it's difficult. And they didn't ship many things that are widely used besides ChatGPT. And so here, I think one thing that we like to do in open source is ship demos. They look good. Like here, I have this framework and look what I can do. But we need to go a step further if this scenario comes true. And I actually think this might be one of the most likely scenarios here. And we need to really have solutions that work for businesses, solutions that are actually useful for individuals. A lot of how AI is used today is we try to figure out what to do with it, but we are not using it so much in our everyday work. There are some applications where it's very useful, but it's not as widely used as you think it would be after these large successes. And then also sort of mirrored, we want to have solutions that really work and that really matter in the real world. I think that's important. If you want to lead, you need to show that you actually can make a difference. And that is basically, we want to go beyond demos. Okay, that's everything that I have on this. Just here, the facets again, all sort of brought together. So I have a little bit more time. And other thing I wanted to talk about is a couple of things that I sort of learned and observed in the last couple of days. And so there was a PyTorch conference, and I was just amazed by how many people presented such broad sort of solutions with such deep technical depth. And so when I think about myself and sort of my strengths, it's like I'm a good CUDA programmer. I'm a good engineer, and I know a little bit about research. And if I put all those together, it led to bits and bytes and a couple of innovations. But if I look at other people, they have so many strengths, and they know so much things about technical bits that I have no clue about. And so when I think about success, it's about combining your strengths to make something unique. And you don't need to be the perfect CUDA hacker to have success. We are here for CUDA programming and systems programming, but you can take parts of that and combine it with the strengths that you already have. And I think that that's very powerful. So if you're not the best systems programmer or not the best CUDA programmer, that's okay, because you have other strengths. And so think about that, how you can use it. And there's so many ways how you can contribute to open source, and that's quite powerful if you use your strengths. The other thing I want to say is, if you sort of see things like QLoRa and bits and bytes, it looks like, oh wow, there's like these big successes and there are these geniuses that build these things. But I failed a very long time. I learned CUDA for 7 years. I had many open source projects that absolutely failed. And Bits and Bytes is not my first open source project. In my PhD, I did 4 years of research, and all my research projects failed. And it took some time until I got there. And so if you fail, don't see it as you are a failure. This is normal progress. It's really hard, particularly what you guys do, CUDA programming and systems programming. It's very challenging. And so don't be discouraged. It's a lot of hard work. You need to gather the experience. You need to use your strengths. But eventually it will happen. There's a little bit of luck involved, and there might be a long streak of sort of failures, but keep up your hope. The other thing, I think that's also related to that, and just seeing this entire community is just amazing. When I was doing CUDA programming like 7 years ago, it was like I was alone. And now there are so many people you can turn to. You can build a community. You're not alone, CUDA mode in the darkness, and you're alone in your room. You're like here with other people. And so I think that's amazing to have this community. And I think there it's also important to just stick together and really support each other, care for each other. I think that's one of the main sort of values of open source. We are not competing, we are collaborating, coming together. And how I can see it for myself, there's a long streak of failures that many people go through. People will try and fail, and so be kind, support each other. I think that's important. And yeah, I think those are my learnings from open source and my learnings from the last days. That's everything that I have. Thank you so much.
I'm really excited here to welcome Professor Wen-mei Hwu. So I think nobody needs an introduction for this guy. Almost everybody have read his book or heard about him on some or other way. But I have a privilege knowing him for various reasons. He's my academic father. I did my PhD with him. He's my current manager too, so I have to be careful on what I say. But more importantly, I think he's a very fun person to work with. We call him, in short, Humble Wen-mei. So we'll go through some of his career things that he has done. It's very interesting. 4 decades, 3 decades of transitions. We'll cover some of them. Please.
Okay.
To give a brief history about the kinds of work that he has done, it's very interesting. For those who do not know, most of the people know about his work on the PMPP textbook, but most of your computers that are working today do out-of-order execution. And yeah, it's his PhD thesis that actually perfected out-of-order execution. So if he had not written that HPS paper and not went to Intel to perfect the out-of-order execution, none of your computers would be working today. And this was his first decade. Then in the second decade, he decided to move towards compilers. Then he introduced hyperblock, superblock concepts to compilers that are there in almost every compiler that are being used, almost every place. Third decade was about CUDA, and now he is into his 4th decade, looking into something even amazing. We'll talk about that. So, Wen-mei, I think the biggest question that I always wanted to ask for like 7 years now, how did you pick those ideas to work on? Like every single decade, you picked a problem that's fantastic, and that problem did not even exist at that time. And you worked on the problem, you figured it out, and you started solving it. But how did you get those ideas in?
Okay, luck.
4 times.
Couple things. When I was a grad student, I listened to the great graduate student talk at the beginning of the session, and I was at UC Berkeley in 1983, and that was a very, very interesting time, almost identical to what we're experiencing today, but in the hardware. Okay, so the chip integration is getting to the point where we can start to build. We're talking about incorporating enough transistors and a whole processor, right? A whole processor on the chip. And that was the time where people start to debate on various things. For those of you who know the history, the RISC project from Berkeley was extremely influential. They asked a very important question. How do I squeeze enough transistors into the chip to build the simplest possible processor so that I can have the first successful commercial product? A lot of grad students contributed to it. Dave Patterson and Randy Katz and Alan Smith and various people contributed to that. And the industry took off from that point. I asked a little bit different question. So if Moore's law is really right, in 5 years, in 6 years, we're not going to be talking about squeezing things into a chip. We're going to be talking about how to make these chips real, right? And so we started to look at the history of mainframe and think about why some of these things failed. And then everything pointed to exception handling and interrupt handling. IBM tried again and again, failed. So I said, okay, that sounds like an interesting question. So if we can get it to work, 10 years from now, people can build a real processor with enough transistors to do this. And it's just luck. And we had enough, people at Intel who got really interested in this, and Bob Colwell was building P6, and then he hired one of my students from Illinois and some of Yale students, and they figured out some of the things we actually didn't figure out. Okay, so and that's history, right? So this collaboration thing is incredibly important. We cannot figure out everything ourselves, right? And some things we just can't figure out as a person, but as a team, as a community, someone will figure it out. And everyone said that this cannot be done. By the way, when I give a talk, Mark Horowitz came to me afterwards and said, nobody will ever build that processor. Okay, and that was the year when I was interviewing for job. Okay, so it was, it was very, very, very discouraging. On the other hand, if you get enough good people interested in that same problem, and sooner or later someone will figure out, and at that point you can take some credit. Okay.
Humble Wen-mei, as always. So I think the key message that you're trying to tell is work on the hardest problem. Don't worry what the outcome is. Try to solve the most hardest problem and work with the community, build a community, and grow with the community. Well, thank you. That's a very nice, interesting insight. I think we pulled some questions together before the start of this event, and the most important questions everybody asked is like, when is your next edition of book coming, and what is it going to contain?
Okay. Every book, every edition ruined one of the Thanksgivings. So this one is probably going to do the same thing. So we are targeting end of the year. So that's why every edition ruins one of the Thanksgivings for all of us. But that's what it is.
Okay. What is the new book is going to cover? What are you hoping to cover in this new book?
Yeah, GPU computing advanced tremendously, right? Now, there are several things that we obviously did not cover in the first 4 editions. The multi-GPU aspect is, blatantly missing, and now it's so mature and so important for every use, every data center now, right? So the multi-GPU NVLink kind of paradigm, or multi-GPU, the data center paradigm. And there are all these important problems in terms of the how you actually pull together GPUs for, let's say, distributed matrix multiplication and so on. And it has been really undercovered in terms of just the intellectual. What's underneath this? What motivates the NVLink 72? And a lot of people don't realize some of the underlying forces. So we're trying to explain these things so that people can understand. And there are many other types of algorithms that we did not feel that GPUs were good for, but with the cooperative groups and so on, some of these new algorithms become very, very efficient. So we're beginning to phase out some of the older material and begin to put in some of the new things that will be more useful for future GPUs.
One of the requests which Wen-mei has for all is please share your feedback on the book. Suggest what topics are missing that can be included. So talk to him afterwards so that we know how we can improve the book. You brought about a very interesting response on the out of order and how things evolved. If I think about now the current generation of LLM, there's a lot of talk about we can create out of order execution kind of models using agents, co-pilots, and also there is an interesting thought about can I create a LLM OS kind of a thing. What do you think from the GPU side and also from the AI side? What things requires to evolve to enable something of this sort? Do you think we will be there in some time? Or I want to hear your thoughts on that.
My honest answer is I don't know. So the couple things that I think will be important, when I was talking to some of the teams here, we already know some of the deficiencies. For example, the CPU side of things, the driver and so on. The CUDA driver is very, very old now. So it doesn't even have enough of the dependency capabilities and asynchronous capabilities. So many things are done synchronously. And it's time for a major revamp. So when we start to talk about LLM operating system and so on, if we don't have that foundation in the driver, these things are not going to end well. When you build something on top of a little gelatin, it's going to just fall apart, right? So and another important part is that when we think about communication and when we think about how to coordinate these multi-GPUs and so on, our memory consistency model, our synchronization primitives, some of these things really need to be rethought. And in the old days, all these things belong in the kernel mode, not the GPU kernel, the operating system kernel mode, privileged and protected. But in the future, these things need to become democratized. These things need to go into the user mode. But we all know that when it comes to the user mode, there are a whole slew of new problems that we need to make sure that we understand so that we can build real products out of it.
Which is interesting. So every time, this is a common thing that we have constantly observed. After writing many CUDA programs, one thing that we always ask is that when CUDA program does not work really well, the first question I often ask is like, okay, have you seen your CPU program? Is CPU doing the real job or not? Amdahl's law, like Prydao was saying in the morning, Amdahl's law always kicks in. Interesting. The thing is, we are also seeing you are actually hitting your 4th decade of your doing research. So he has pivoted every decade. So what are you pivoting to? So that we know the kinds of problems that we have to think about from the community side, that we have to be excited about, that we have to work together to solve problems. So what do you think is the next decade of problems that we have to work on?
Again, I don't know. I think if anything, coming to this kind of event, really teach me a lot of things that honestly I feel old in this audience. Okay, everyone here is young and energetic. So one of the things I learned is that when I supervise grad students, the first thing I do is to make sure that I don't get in the way, right? So whatever you do, be bold and be fearless. You're going to be making mistakes. Okay. Having said all that, I do have some personal view about this, and then in 10 years, hopefully, we can come and talk about whether these views are right or wrong. I feel that we're fundamentally doing something that is a little bit, I would say, questionable. We're trying to train all the data into these models, and when the data gets bigger and bigger, these models need to get bigger and bigger. And we're trying to regurgitate information or whatever you want to say, regenerate information as quickly as possible out of the huge training data that we train into the model, right? So that's why we have all these, the good, techniques like speculative, the inference and so on. But I think we need to take a step back at this point and think about this. What if we can real time, for any kind of query, we can real time gather all the information necessary to answer that question in milliseconds, okay? So, let's think about it this way, right? You can use the model to try to, to regenerate the information you used to train the model. And we used to think that this data is so expensive to access and so slow from the object stores and all that stuff, right? But if in the next few years you start to see systems where you can get a gigabyte's worth of information for any particular query out of 10 petabytes of data or 10 petabytes of things that Google and so on currently only serve from the web search, right? And the information can be presented in a way that can be fed into some kind of model that is trained to be able to take that information and synthesize, summarize the right thing, right, to answer the question, rather than trying to get everything from that model. And I believe we'll be taking a different course in the future. And the data, no matter what, how good we are, we always need to go back to the facts. We also always need to be able to debug some of these things. And having data access capability, I believe, will be the next step for these models. And we already see RAG now, right? But RAG is just a start. And real-time access to the bunch of things that we currently only can regenerate from the models, I believe will change the course of this whole revolution. So in 10 years, we'll see.
Data access is a key problem that we have to solve. Earlier today, and also yesterday, Stephen Jones was also speaking. I/O is a big problem that we have to address. And the more we increase our compute resources, I/O is going to be the bottleneck that we have to consider thinking about. There is a lot of interest and also challenge that comes in when it comes to education. You have been an educator for several years. With the introduction of ChatGPT, language models, now many questions can be easily answered by the model itself. So what is the role that you think from education standpoint of view? What is how should the education should transform in the new language model era?
Okay. Let me say it this way. I'm not an educator. I see myself as a teacher. There's a difference between teaching and teacher and educator. Educators need to think about the whole thing. When someone asks me, after 33 years teaching at the university, do you miss teaching after you moved to NVIDIA, right? I said, yes or no. I miss teaching in the sense that when I explain something and I see my students start to light up, and that's what I miss. What I don't miss is to try to come up with the final exam questions and then grade the final exam and then catch the cheaters and then figure out what to do with the cheaters. Every semester I have plenty of supply of those, right? So here's the thing, right? The cheating is always going to be there, right? And with these tools, cheating will be easier, right? So I don't know how to solve that problem. And on the other hand, I believe that if we teach students in a way that they become truly interested in the subject, a very good big portion of the students will never cheat. Okay, and that's what I believe. But can we get to that point? And maybe we should begin to have some of the boring parts of the education taken care of by the models, right? And and then have the real teaching part to deal with some of the real subtleties and the real difficult part of things, so that maybe we never have to deal with cheating again. So let's see.
Very nice. We are about almost time. Professor Hwu, thank you so much for sharing your insight and experiences with us.
Thanks for having me.
Your work had an incredible impact on everybody's life here. Everybody have some other way have read your book or extract of your book so that they made far progress in writing CUDA kernels today or in several weeks before. And I'm sure this same work is going to continue to impact everybody of our life for many, many more years. Thank you so much for everything. So
thank you.
This is a token of appreciation from CUDA Mode. So
thank you.
Thank you.
Thank you.